Okay, YouTube, in our previous video we explored this new number or constant that we call E, or Euler's number. And we said that E approximately is about 2.718, but it is a particular constant that we like to pay attention to. And without going too much into detail, it is an interesting constant when we deal with exponential growth and decay functions. And so, at least with respect to exponential, we would say that growth or decay, what experience we have with these functions so far is that they come in these packages that look like this. And so most basically, we'd see that y equals a times b to the x, where we first focused on just b to the x, but we'd say a times b to the x, where we kind of expanded this definition to say, well, then it's really just a times 1 plus or minus some rate to the time, or I'm still going to use x here. But essentially, these were our two really basic models here, where in each case we can see that we have some base to an exponent here where our variable is in the exponent. And so these exponential functions here, where these are both kind of like our b value, we have some arbitrary base, whereas what we're going to look at in this video are what we call natural base exponential functions. And that is to say, natural base exponential functions, we call this the natural base, is the name of E. So the natural base gets its name because when we talk about natural base exponential functions, then what we're really talking about is an exponential function that looks like an exponential function. That is to say, it has some initial value, and that's what we always are kind of identifying what this a value represents. And so let's write on a note here. This is our initial value of something here, times the base, which in this case was b, or b could be written as 1 plus or minus some amount of rate of growth or decay. But we could say that if this base were in particular the value of E, then what we have all of a sudden is a natural base exponential function. And so because E is pretty much glued, we say that this is the natural base. This is about 2.718. Let's see if I can write this more clearly. 2.718-ish. Okay, and that's always a positive number that's bigger than 1. Then we would say that really what you get is some function that's always going to be a growth function, right? Because when our base is bigger than 1, then we must have growth. And so to accommodate for this, the other way that we represent a natural growth function is that we put our rate of growth or decay is up in our, I guess, our exponent here. And so we say y equals ae to the r times, or to the power of r times x here. And this is all in our exponent right here. And so we're going to delineate on a few things here, but we'd say that a function of the form y equals ae to the rx, where our base is just the natural base here, is called the natural base exponential function. And we want to identify a few things here. So hopefully I can sketch on this here. Oh, that's better. We say, but in both cases, what we want to identify is that our a value here, let's try this again here, we'd say a is positive. And that is very apparent here, both in this first case and in this second case here. And so we're starting with some initial value here, a. And so that's another thing I want to write here. A is the initial value of some quantity. And so when we talk about some quantity, okay, of course this could be like people, for example, people, if I could spell people. People, like bacteria in a colony. We could say radioactive elements, okay, like how much it contains of some radioactive element. But we say the initial value of some quantity here, we're going to say r. R is our rate of growth. And so you're going to see that there are two different situations here. One where R is positive. So we say R positive here. You can make a little note somewhere on your paper there. We say R negative. I'm just going to kind of squeeze it in here. In the second case, but we'd say R is our rate. And so a few things we're going to say about this rate is often given as a percentage. Given as a percentage. And also when we deal with it, in terms of a problem like this, we want to represent it as a decimal. So represent as a decimal. So that is to say, for example, we say 50%. We would want to write this as 0.50 would be a good example there. And so we would say that x here, our x variable, x is often time. is often time. So from time to time, no pun intended, you'll see instead of y equals ae to the rx, you'll see y equals ae to the rt. But we often represent t, or time, along our x-axis. And so you could look at this as a t sometimes also. But you'll notice where r is positive, we have an exponential growth function. And where r is negative, we have an exponential decay function. We could say that all natural base functions look like this. And we'll know if we have growth or decay just by looking at whether r is positive or negative. So we say the graphs of these basic functions, y equals e to the x and y equals e to the negative x here, are shown. And you can see that one really here, we have a growth function here. This is y equals e to the x, and we have y equals e to the negative x is given here. But what I want to point out about both of these is they both consistently go through this point here. And let's switch over to red here, 0, 1. So this was very much in common, or is very much in common with our actual exponential growth and decay functions we've seen so far. And the reason why this is the case is because recall that when you plug in 0 into an exponential function like e to the 0, we would get 1. So regardless of whether you had e to the 0 or e to the negative 0, you would get e to the 0, which is 1 as an output here. And so we're going to see that we get this 0, 1 point here on the graph of at least y equals 1 times e to the x here, or 1 times e to the negative x. But you can see that where we have a positive 1 here, r equals a positive 1 here, we have a growth function. Where r equals a negative 1 in this particular case, we have a decay function. And so what I would say is to sketch our graphs. Okay, here are the things we're going to want to identify. One, the horizontal asymptote, and where that exists. So recall it's on the x-axis here, and on both of our graphs here we have this horizontal asymptote. Goes on forever and ever. It's this imaginary line here that we represent with a dotted line. But it represents the fact that our function never quite truly gets to a height of 0. And this is our horizontal, okay, asymptote. The other thing we want to make sure that we represent, number 2 here, is the y-intercept. And so in order to find this here, we plug in 0 for x, or you could say for time, I guess. But we would say that we would always have an output of 1 there. And then we would say for number 3 here, find 1 extra point. Let's make this 2. 2 extra points on the curve to the left and right of the y-intercept. And so what we're going to do essentially to graph these is recognize that we have this basic shape of our growth or decay here, and that they proceed through this point 0, 1, but we'll plug in a point to the left of this, an x value to the left of this, like negative 1 here and positive 1 here, in a table to come up with some extra values on our graph so that we could come up with the basic shape more accurately here. So we could see that, for instance, on this next page, if we're going to graph some exponential functions that are natural base exponential functions, then what we know is that we have some functions that are this initial amount times e to the rx, where r is our rate and a is the amount that we're starting with on something. So it says tell whether each function represents exponential growth or exponential decay, and then graph the function here. So we see that both of these functions here have a natural base on their exponent. It's just that in our first function here, the interesting thing is that our r value is the coefficient of x, and we recognize that r is 1. And so the characteristic that we're trying to indicate is whether it's positive or negative. Because it is positive, then this would indicate that we have a growth function with respect to a natural growth or decay function. Whereas over here, we see that r is equal to negative 0.5. I'm going to write negative 0.50, and that this is negative. Okay, so this would imply that we have a decay function here. So for at least for our first graph here, we have this thing that's going to grow, and for our second graph, we have this thing that's going to decay like this. So at least we know this basic shape. Now, with respect to graphing the rest of this, what we're going to do is something that is wise to do, but is to create a table of values here. And so the 3 x values that I would always indicate you should probably use here, unless you've got a graph that's translated, which in that case we would graph the parent function anyways, but we would plug in 0 here for our x value. And that's because we want to find our y-intercept, and we'll also plug in negative 1 and 1 for our x values here. And so this will give us at least a good indication of what our graph looks like around the middle here, which, as you've seen, is the most interesting part of our graph. Of course, as we go, say, to the far to the left or the right, it's either very much growing or very much hugging the x-axis. So in the middle here, we'll get a good idea what this looks like. But let's go ahead and plug in some x values here and graph what we see. We say 3 times e to the first power or sorry, 3 times e to the x power here, if we're going to plug in, say, 0, let's start with this. If we say f of 0, we would get 3 times e to the 0 power here, which is really 3 times 1, which gives us 3. So you can see that we do indeed start at 3, which is our initial value at the initial point here, 0, 3. Now plugging in 1, we say f of 1, we get 3 times e to the 1. Now this is something where we're actually going to need to use our calculators to get a decimal value for. But 3 times e to the first, recall that your e to the power button is right behind this ln key traditionally. So we're going to hit 3 first, of course, 3, and then we're going to hit second ln, which gives us e to the power of, and we're going to say e to the power of 1. So typing this in, looks like we get 8.15-ish, and I'm going to go ahead and type in now the same thing, except for this time I'm going to type in 3 to the power of negative 1. So we say negative 1 here. And so we would see that we get I'm going to say 8.2-ish, 8.2-ish here, and going back when we plugged in negative 1, we get 1.1-ish, so 1.1. And so going back and graphing these points, we could see that at negative 1 comma 1.1, this would be this point about right here. Now I'm not going to label it on my graph, but only because I gave it in this table. If you don't give it in a table, you have to label it on your graph. But we say 1 comma 8.2, we say 1, 2, 3, 4, 5, 6, 7, 8. 8.2 would be in this neighborhood here. So you can see that with our exponential function here, this is a growth function, we would have our horizontal asymptote at our y-axis. So we say y equals 0. This is our horizontal asymptote. And we could see that going through this, we could get a really nice growth curve here going through this. And our graph, we're having to put arrows on this, looks like this there. And so we could say, last but not least, I didn't ask for this, but let's go ahead and identify it. We say domain and range. With respect to domain, it looks like it's going to cover every x value from left to right. So we'd say all x values, all real x values. And then we'd say for y values, we say all y values greater than 0. We hit on the y-axis here. So for our second graph where we have a decay function, we definitely need a calculator on this one. But going ahead and starting with plugging in 0, we'd say f of 0. We get e to the negative 0.5 times 0. Now, as you know, anything times 0 is 0. So we get e to the really negative 0, which is e to the 0, which is 1. So we get 0 comma 1 on this graph. But one thing I want to point out here is because our a value, quite technically out in front, is 1, that means that we had to start off with an initial value of 1, just like here we started off with an initial value of 3. And if you want to know what I mean by initial value, I mean right when we started. So now the rest of this graph here, let's go ahead and plug in the rest of these points. We say f of 1, this would be e to the negative 1/2 times 1, or in other words, e to the negative 0.5. So typing this into the calculator, suppose we could say second ln e to the, and I suppose we could even type this in negative 0.5, negative 0.5. Let me try this again here. 0.5 times 1. And that way, when I hit enter here, I go back and type in second enter. I go and put in, I suppose I could do a negative 1. So I'm going to use my insert option this time. We say here are our values. So we could see that at least at 1, it's at about 0.6. At negative 1, it's 1.6. We have 1.6 here. Let's see if it'll write it in there. And then we get 0.6 here. So interestingly, you could see that to the left of 0, we say at negative 1 for an x value, we're at a height of 1.6, which is more than 1.5 by just a little bit. And then to the right, we're at about 6/10 off the ground. You could see that graphing all of this in, this is our exponential decay function. We could see that the amount of what we have over time here, this is our y equals 0 horizontal asymptote, is decaying, and we could see how a curve would maybe come through this, and I could see how it's kind of like not very steep, maybe a little wider in this particular case. So our domain, as with all of our exponential functions, looks like is all x values, all real x values, and our range here, again, it's all values on top of the y, or the y equals 0 horizontal asymptote, so we say y is greater than 0. Cheers.